this clip and basically the rest of this chapter is all set up for the spectral theorem. The spectral theorem characterizes the self-adjoint operators as the operators which are diagonalizable with an ONB. So in other words, those for whom the eigenvectors can be chosen to form an orthonormal basis. That's over R. Over C, it turns out that it's not the self-adjoint operators, but the normal operators, which are pretty close. We're going to talk about them actually in the next clip. But the spectral theorem is pretty important, and it takes a bit of build-up. So that's what these results are working towards. Okay, so first off, if we're working over C, then if TV is always orthogonal to V, it has to be the case that T is equal to 0. So now notice that this is false if we are working over the reals. And so you can consider rotation of rotation of R2 by pi over 2, right? Like if we just do a counterclockwise rotation by pi over 2, then every vector is going to end up pointing orthogonally to whatever it started off being, right? So you're going to have TV orthogonal to V everywhere, but that's definitely not the zero transformation, right? But the thing that jumps out at you is like, oh yeah, but that's also our canonical example of a transformation that does not have real eigenvalues, right? And here we're talking specifically about using F equals C. So yeah, that's not a coincidence. Okay, so the proof is not really especially enlightening. It just has to do with the fact that for any U and W in our vector space, we can write TUW as a linear combination of terms of this form. So specifically, we have the following identity. TU against W can be written as 1/4, and then we're going to have the real part, which is going to be TU plus W, U plus W minus TU minus W, U minus W. So that's the real part. So I'll put a parenthesis around it. Plus, and then we've got the imaginary part. So this is going to be T applied to U plus IW, U plus IW, and then minus T applied to U minus IW, U minus IW. All right, so there's nothing really to be seen here. It's just if you take the right-hand side of this and you crunch it out, eventually it boils down to inner product of TUW. That's it. So the key point, though, is that here this is like TV comma V, this is TV comma V, this is TV comma V, this is TV comma V. So if TV comma V is equal to 0 everywhere, then everything on the right hand side is equal to 0, so the one on the left is equal to 0 as well. And so then that vanishes everywhere. And so in particular, if we take W to be TU in this expression, because we've got the freedom to choose U and W to be whatever we want, then this expression right here becomes norm squared TU. So then TU is the zero vector for every U. In other words, T is the zero map. Okay. So that's our first result. Our next result is to extend this to the real case, in which case we need this extra hypothesis that it's self-adjoint. So if you have something that's self-adjoint and TV is orthogonal to V, always, then it's the zero function. Okay, so so we proved this for C above without that extra hypothesis. So suppose we just need to. So suppose that we're now working over the reals, because that's the only case that we have left to work with. And notice that for the reals, the argument above does not work because it involved using all of these complex numbers over here to make the computation work out. So if you try and do the same thing, and that's basically how this proof works, it doesn't quite work as it is right there. But actually what happens is we get TUW is equal to, and then we just have the first part. So this is TU plus W, U plus W minus TU minus W, U minus W. And then you're probably going to wonder and say, like, well, wait a minute, it looks like it just got simpler. Why did we need the extra hypothesis or anything? Well, it turns out that when you do this calculation right here to verify that this is true, you have to use TWU equals WTU, or things do not cancel out in order to simplify the right-hand side into TUW. So that's where the self-adjointness comes into play. But then, once again, with this identity, then everything on the right looks like TV comma V, TV comma V, and so the rest of the argument proceeds just like it did in the last theorem. Okay. And then our last result, so let's just swing this up a little bit, is that if TV against V is always real, then that implies that T has to be self-adjoint. All right, so proof. Okay, well, so we showed that eigenvalues were real by showing that lambda minus conjugate lambda is equal to 0. So now we're going to see what happens when T minus T star is 0. That's the way the argument proceeds. So let's take T minus T star and we will apply it to V. And then take the inner product with V. And so by linearity, we have TV V minus, and then I've got T star VV, and then I can move that T star to the other side, so this becomes TVV minus VTV, which is equal to TVV minus TVV conjugate. Okay, and so this, the forward direction right here is going to use 7.14 from what we saw before, because now if it's always real, then that means this is always equal to 0, which means t is always equal to t star. That's by 7.14. And then if we go back in the other direction, if t star is equal to t, then the left side of this expression is equal to 0, which implies that the right side of this expression is equal to 0, and hence TVV has to be real. So, by the way, this expression that comes up, so if we take, let's, oh gosh, what's a good name for here? We'll call it R. R is the set of TVV where V can be whatever you want. This is what's called the numerical range of T. And so this is a subset in general of the complex plane. Maybe I should have included that when I wrote the definition. And it tells you a bunch about the operator. If the operator's bounded, for example, then this set will be bounded. If the operator is self-adjoint, then this set is going to be a subset of the reals. It also turns out that that R is always, no matter what, convex. So if it's a subset of the real line, it's going to look like an interval of some sort. If you're interested in learning more about this, I'm just going to volunteer a couple of my colleagues. Dr. Patton does a lot of research on numerical ranges of operators, and I think Dr. Retzik also does. He seems to be knowledgeable about it, at least. And there's a few others that also, I'm not sure if they do work in it or if they just are knowledgeable about it, but Stankus and Shapiro and Gu all know a fair bit about numerical ranges. Maybe Robbins also. There's a bunch of people in the department that are interested in this thing, and there's a bunch of open problems that are fairly accessible. So if you're interested in doing like a student research project in mathematics, you might ask one of them about this. I'd start with Dr. Patton.